Hello students, let us continue about standard Ethernet. In standard Ethernet, the addressing format can be discussed here as follows. Basically, each Ethernet network is having its own network interface card, which we consider as NIC. This NIC fits inside each and every station, which provides the link layer address of the station, and the addressing is of 48 bits of length, and normally it is called 6 bytes, and the representation is for hexadecimal digits separated by colon. So each hexadecimal digit forms a 1 byte of information. So there are 6 bytes of addresses separated by colons. So this is termed as an Ethernet MAC address or a link layer address, and this is provided by the NIC, that is network interface card, which each station possesses. Now basically the transmission of the address bits can be explained here as follows. Consider as an example the Ethernet address is 47:1B:2E:08 followed by EE. Show how this address is sent out online. Now the information which comprises of the address will be sent from left to right byte by byte. So 47 is 1 byte, and it is the first byte which has to be sent out. While transmitting, the first byte is transmitted, and in the first byte the least significant bit LSB is sent out first, and most significant will be sent at the last, because by knowing the least significant bit, whether it is 1 or 0, we can decide whether it is an unicast address or it is a multicast address. Because whenever it is 1, it is considered as a multicast address, and whenever it is 0, whenever the LSB is 0, we consider it as unicast address. So when sending an address, the address will be sent byte by byte from left to right, and in each byte the LSB is sent first and the MSB is sent at the end. Now there are different types of addresses, as I told: unicast, multicast and broadcast address. If it is unicast, the frame comes only from one station, and the destination could be, again, it can be unicast, it can be a multicast, or it can be a broadcast. And if the least significant bit of the first byte is 0, it is unicast, otherwise it is a multicast. Now this is an example to show the multicast and unicast address, where the first bit, that is LSB bit, if it is 1, it is considered to be the multicast, and if it is 0, it is considered to be the unicast. Note that the way the bits are transmitted is the first bit which is transmitted or received, and the broadcast address, basically it has all the bits are 1. The broadcast destination address is 48 ones. Okay, so each byte comprises of FF. So all the 48 bits or 6 bytes will be 1 for broadcast. Now define the type of the following destination address. Consider the first one. You need to tell what type of address it is. By looking at the second digit of an hexadecimal number in the given address, it is A. A is in binary stands as 1010, which is even number. When it is even, that is 0 is the least significant bit, I can clearly tell it is a unicast address. Whenever it is in the second address, the second digit is 7. So 7 is an odd number, and you can tell it as a multicast address. In the third address, all the bytes are FFF. So the 48 bits of the address comprises of all ones, which you can term it as a broadcast address. This is how we can identify what type of address are. So in case of unicast transmission, all the stations will receive the frame, only the intended recipient will keep, others will discard the frame. In case of multicast transmission, all the station will receive, the stations that are a member of the group keeps that, remaining will discard. But in case of broadcast transmission, except the sender, others will receive, all others will receive, and all stations keep it and handle it apart from the sender. So these are the different types of transmission, which are nothing but unicast transmission, multicast transmission, and broadcast transmission. Now to proceed with the access method of standard Ethernet protocol, it's a broadcast network. We need to use an access method to control access to the sharing medium. Let us consider that A wants to send information to D. Here A wants to send information to D. Now in such situation, there is a sharing of the medium would occur. Now to proceed, A has to send information to D. Now what is the procedure that it should follow? Initially A senses the channel or a medium, which we call it as a carrier sense. By how it senses, basically station A, it measures the level of energy for a short period of time, which is normally less than 100 microseconds of time. If the level of energy is 0, then it is considered to be that medium is idle. Medium is idle, that is, no station is sending the information. Say a station A, it interrupts this situation as idle medium, it starts sending the frame. That means within the 100 microseconds of time, station A has sensed the channel and it finds that its energy level is 0, and no other, thinking that no station is sending, A starts interpreting and it sends the frame. On the other hand, if the signal level energy is not 0, it means that the medium is being used by another station. So A continuously monitors the medium until it becomes idle for 100 microseconds. Since some other station is occupying that channel, A will continuously monitor the channel for 100 microseconds. It then starts sending the frame in case A finds the channel is idle. However, A needs to keep a copy of the buffer until it is sure that there is no collision and the channel is idle. Okay, so for both the condition, A needs to buffer the content. And in case any collision occurs, if at all any collision occurs, then A has to resend the same frame, so it has to save the information in its buffer location. The medium sensing basically does not stop after A started sending the frame. Say for example, A has found that within 100 microseconds of time the channel is idle and starts sending the frame. Now A needs to send and receive continuously. So there are two cases may occur. First, A has sent 512 bits and no collision is sensed. Thinking that the energy level did not go above the regular energy level, the station then basically it is sure that the frame will go through and stop sensing the medium. That is the one case. If we consider the transmission rate of the Ethernet is like 10 Mbps, since it is, we have chosen it as a standard Ethernet, right? Standard Ethernet data rate is 10 Mbps. And how many bits we are sending? We are sending 512 bits. So now what is the time that it takes to send all these 512 bits? This means that it would take 512 over 10 Mbps. So which is equal to 51.2 microseconds to send out the 512 bits. If at all collision were to occur, it should occur by the time the sender has sent out 512 bits. A second condition, like A has sensed a collision, say for example before sending the 512 bits. This means that one of the previous bit has collided with a bit sent by another station, so the energy level has reached to the maximum. That is not a normal energy level. In both the cases, station should refrain sending and keep the frame in their buffer for resending when the line becomes available. Now these are some of the topology Ethernet LAN. This is a LAN with bus topology using a coaxial cable where multiple devices are connected using a drop line and a tap here, and these are the ending and ending terminals of the bus network. And basically this is an star topology where it comprises of an hub and multiple devices are connected to this hub. Any node in the particular star topology wants to communicate has to interact with the hub, and hub will communicate to the device. So these are the different types of topologies of Ethernet LAN. Now, how do you measure basically the efficiency of a standard Ethernet? The efficiency is measured, basically it's a ratio of the time which is used by the station to send data and to the time the medium is occupied. Say for example, I have occupied the medium for about 100 microseconds, but I have used only 10 microseconds of time to send the information. That means station has utilized only 10 microseconds. Now what is the efficiency of the standard Ethernet? The efficiency is calculated by the equation efficiency is equal to 1 over 1 plus 6.4 into A, where A is nothing but the number of frames that can fit on the medium, and it can be calculated as it is a propagation delay over the transmission delay. There is a difference between a propagation delay and transmission delay. The transmission delay is the time it takes a frame of average size to be sent out. Remember, transmission delay is the time it takes the frame of average size to be sent out. Propagation delay is a time it takes to reach the end of the medium. So transmission delay and propagation delay are different, and it is the ratio of propagation delay to the transmission delay would gives the A. Now using this you can calculate what is the efficiency of a standard Ethernet. Now as A value decreases, the efficiency would definitely increase. This means that if the length of the medium is shorter or the frame size is longer, efficiency increases. In ideal case, if we consider A to be 0, then efficiency would be around 1 or 100%. Consider the standard Ethernet with a transmission rate. They have given a transmission rate of 10 Mbps of capacity, assuming the length of the medium is 2500 meter and the size of the frame is 512 bits. The propagation speed is given normally 2 into 10 power 8 meter per second. Now the propagation delay is how much? This is the normally the propagation speed of a signal over a length of a medium is 2500. So you get a propagation delay of 2500 into 210 power 8 would give you 12.5 microsecond. So this is the propagation delay. Now for a transmission delay, the time you can consider it's like 512 bits is the size of the frame, and the transmission rate is 10 Mbps. So 10 into 10 power, that's 10 power 7. Then if you consider it as 51.2 microseconds. Now what is A? It's a propagation delay over the transmission delay would gives what is A. A is equal to 12.5 divided by 51.2 microseconds would give you 0.24, and the efficiency is 39%. 39% is out of 100%. 39% is the time which has been utilized by the station, and the remaining 61% the medium is occupied. The medium is occupied, but only out of 100%, 39% has been utilized by the station. The remaining it is not. Okay, so you could just consider that the 39%, which is considered as a moderate, which means that the 69% of the time medium is occupied but not used by the station, and the 0.24 is the frame occupies the whole medium in this case, so 0.24. Okay. To proceed with further, the standard Ethernet, how can we implement? There are different types of implementations of standard Ethernet. Earlier there were four basically the types of standard Ethernet implementation, which became popular actually during 1980s. The nomenclature is provided like 10 base X. 10 stands for the data rate, that is 10 Mbps, base stands for the digital baseband signal, and X stands for the type. Basically here what type of the cable or what is the length of the cable is defined at X. Say for example here, if I could represent in place of X as 5, it means that I am using 500 meter of cable. If it is 10 base 2, then 2 if I represent 2 for 185 meters of length. Or say for example the type of cable, that is T. If I write it as 10 base T, in place of X it is replaced with T, then T indicates that it is an unshielded twisted pair cable. And for if it is F, then it is for fiber optic cable. So the different types of nomenclatures are provided, and basically four types of standard Ethernet implementation, among which they are 10 base 5, 10 base 2, 10 base T, and 10 base F. And this 10 base 5, the medium is thick coaxial cable of medium length, 500 meter, and the type of encoding is Manchester for all the standard Ethernet schemes. In case of 10 base 2, it is thin coaxial cable of medium length, 185 meter, and for 10 base T it is an 2 UTP. It is an type of the medium and of length 100 meter, and for 10 base F it is 2 fiber, which is of 2000 meter. Now to proceed further, normally it is the encoding and decoding schemes which are used here are Manchester. Consider I have an 10 Mbps data which is to be encoded and sent through the medium, and at the decoder end it has to be decoded using the same Manchester decoding scheme, and the data is sent to the upper end. So Manchester encoding, basically at the center data is converted to digital signal using the Manchester scheme, and the received signal is interpreted as a Manchester and decoded into the data. So it is basically a self-synchronous, providing a transition at each bit interval, and the scheme is basically used in standard Ethernet implementations. Further, the different types of implementations are discussed in the next session. Hope you understood the topic. We'll continue this in the coming sessions. Thank you all.